Hello, everybody. How are you all? I hope everybody is doing fine. So, this is me, and I again welcome you in this class. This is lecture number 5 of light. So, let's move on to the next slide and let's try to understand what we will discuss here. So, in this lecture, we will be studying about refraction. In our previous lecture, we saw reflection. So, there are some very similar concepts in both the topics, reflection as well as refraction. This is reflection and this is refraction, and what we have seen yet reflection. So, these are similar topics. The concepts which we studied yet will be used as it is in this topic also. So it will be a little bit easier for you to understand. So let's talk about refraction through a rectangular glass slab. A rectangular glass slab. So this is a rectangular glass slab, and this is a ray which is incidizing, or you can say falling on the surface obliquely. Okay, so this is a ray which is falling on the surface obliquely. Now, if it follows its actual path, then it should be going like this. It should go like this. Okay. But instead of following its path, it is bending towards the normal. You can see this is your normal. What is normal? A normal is a line which is perpendicular to the surface. So this is your normal. And this light ray is bending towards the normal. It is not its actual path. It is not the path which it was following previously. It is its new path. Now, here you can also see that after entering into the air from the glass, it is again bending away from the normal. This is the normal and it is bending away from the normal. Okay. So, this bending of light is known as refraction. If you are asked what is refraction, what is refraction, then you can simply answer that the refraction is the phenomena where a light bends, or you can simply say bending of light when it enters from one medium to another, then this is called refraction. So I hope guys you got my point. This is our incident ray, this is a glass slab, and after the refraction it is bending towards the normal, and this is the second case where you can also observe again refraction, and by this process it is bending away from the normal. So you can see that this ray and this ray is parallel, but you can also observe some shift. This is some shift of ray. This ray was going like this. This is also parallel to this, but there is some distance between these rays. This is called shift, and this is due to the refraction. I hope you got my point. Now, let's move to the next slide. Okay, so in this slide, we will study about the two cases of refraction. The two cases of refraction. This is our first case. This is our first case, and this is our case second. Okay. So, in first case, what happens? This is a light. It comes from the denser medium. This is the denser medium, and this is rarer medium. Okay. Here the particles are little bit close, but here the particles are a little bit away. So this is the denser medium, this is the rarer medium, and here the light is coming from the denser to the rarer medium. So you have to remember that whenever a light enters into a rarer medium from a denser medium, it bends away from the normal. This is your normal. Okay? And this N1 is the density. And here you have to pay attention that the density which I am talking about here is the difference, is different density from what we use generally. Generally, we talk about the mass and volume density, but this is optical density. This optical density, okay? And this is N2. The N2 is the density of medium second, and N1 is the density of medium first. So the density of medium first or the N1 is greater than N2. So that's why what is happening here, the light is bending away from the normal. Now, let's try to understand the second case. So, in the second case, what's happening? The light is entering from a rarer to a denser medium. Here in this case, this is just opposite of case number first. In case number first, the density of first medium was greater than the second medium. But in this case, the density of first medium is smaller than the second medium. And you can simply say that our medium first is a rarer medium. On the other hand, a medium second is a denser medium. So in this case, what will happen? The light will bend close to the normal. This is your normal. And light will bend close to the normal. I hope guys you got my point. And there is another thing also which you have to remember, that the angle of refraction in case first, refraction, or you can write it here, angle of refraction is greater than angle of incidence. You can see it here. This is angle of incidence and it is smaller than this angle R. But in the second case, when light was bending towards the normal, in the second case, the angle of diffraction is smaller than the angle of incidence. Angle of incidence. Now you might be confused that when we were studying reflection, then R refers to the angle of reflection. But here, what we are studying diffraction. So that's why R denotes angle of diffraction. Angle of refraction. I hope guys you got my point. Now let's move on to the next slide and let's try to understand what is there for us. So here we are. Here we will study the laws of refraction of light. It is very important term. Laws of refraction of light. As we also saw some laws of reflection when we were studying laws of reflection, when we were studying topic reflection. But here what we study? We study about refraction. So that's why we have to study about the laws of refraction. So this is a first rule which will be followed in every case of refraction. So what it says, it states that the incident ray, the normal and the refracted ray all lie in the same plane. So this is your incident ray. This is your incident ray. This is your refracted ray. Okay, this is refracted ray. And this is your normal. And I do not need to explain you again what is normal. Normal is a line which is perpendicular to the surface. So these three lines are always lie in the same plane. These three are always lie in the same plane. So now let's move on to the next rule, and that is Snell's law. It is very, very important. Snell's law is very, very important. So what it says? It says that the sine of I means sine of angle of incidence, and sine of R, it means angle of R here is angle of diffraction. Okay, so here this is angle of diffraction. Let me cut it. Okay, so the ratio of the sine of angle of incidence and the ratio of sine of angle of diffraction is always constant. Let's suppose if the sine, if the angle of incidence here is 45 degree and here it is also 45 degree. So what you will write, sine 45 upon sine 45, and it will cut and give you the result 1. So in every case, this ratio will be 1. This ratio will always constant. Okay. So I hope guys you got this point, that what Snell's law states. Now let's move on to the next slide and let's see what is there for us. Okay. So guys, this ratio of sine I upon sine R is also known as refractive index. Refractive index. Okay. As you can see in the previous slide, here also it is written that this constant is refractive index. Now guys, let's see here in this table some mediums and their refractive indexes are shown here. The mediums and their respective refractive index are shown in this table. So the refractive index of air is 1.0003. Refractive index of ice is 1.31. Refractive index of water is 1.33. It is important. Many times it is asked in the examination. Or you will see that there are some questions where you have to use this refractive index, but the value will not be given. So you have to remember the refractive index of air, ice and water. After that, alcohol 1.36, kerosene 1.44, fused 1.46, and turpentine 1.47, benzene 1.50, chrome glass 1.52, Canada balsam 1.53, rock salt 1.54, carbon disulfide 1.63, dense flint glass 1.65, ruby 1.71, sapphire 1.77, and diamond 2.42. Also, you don't need to remember all these, only three, or you can say air to this alcohol is important. So you will just remember this. Otherwise, you don't need to memorize all the other refractive index. So let's move on to the next slide. Okay. So the ability of a medium to refract light is also expressed in terms of its optical density. Optical density has a definite connotation. It is not the same as mass density. This line I already explained you in the previous slide, that optical density which we talk about here is different. Optical density is different from the mass density. Many times students get confused between these two terms. This is different and this is different. So if a optical density of a medium is low, This means the medium is rarer medium. But when it is high, in that case, the medium is denser. Okay, I hope you got my point. The one with the larger refractive index is optically denser, and the other medium of lower refractive index is optically rarer. So, refractive index is directly proportional to the optically rarer medium or optically denser medium. If the refractive index is high or large, it simply means that the medium is denser, and if the refractive index is low, it simply means that the medium is optically rarer. So here the speed of light is higher in a rarer medium than a denser medium. Okay. So guys, it is very simple. For an example, let's suppose this is medium first and this is rarer medium. Rarer medium means the particles are a little bit far away from each other. On the other hand, this is medium second and this is, let's suppose, denser medium. Denser medium means it is optically denser and the particles are very close to each other. So now you tell me that for light, in which medium the traveling is difficult? I think in the denser medium. Why? Because here the particles are close. So the speed of the light will automatically decrease in the denser medium. Decrease in the denser medium. But when it travels in the rarer medium, here the speed is increased. Why? Because the particles are away from each other. You can take an example of a crowded area. So if you are running in a crowded area, so it is very difficult to run. But on the other hand, if you run in a playground where very few people are running, then you can easily run there. Why? Because there is no crowd or the peoples are far away. So that's why it will be a little bit easier to you to run. So the same thing happens with light. When it travels in a rarer medium, its speed is increased, but when it runs in a denser medium, then its speed is decreased. So this is the reason why light bends. Okay, so this is the reason of refraction because of the difference between the speeds in medium. Now, the same thing is written here. Thus, a ray of light traveling from a rarer medium to a denser medium slows down and bends towards the normal. When it travels from a denser medium to a rarer medium, it speeds up and bends away from the normal. I hope guys got my point. Now let's move to the next slide. Okay, so here the formula of refractive index is given. So if you are to calculate the refractive index of a medium, then you can simply figure out this by the help of this formula. So let's suppose this is this, this is a light ray in medium first, and this is bending, and this is medium second. Now let's suppose this is the velocity of the light ray in medium first, and this is the velocity of light ray in medium second. So if you have to figure out the refractive index of medium second, then what you will do, you will simply write down the speed of medium first and you can divide it from the speed of light in medium second. And suppose this is V2. By this formula, by the help of this formula, you can simply determine the refractive index. Okay, and let's take an example here. Let's suppose the velocity of light in medium first is 10 meter per second and velocity of light in the second medium is 20 meter per second. Now if I want you to find out the refractive index of medium second with respect to medium first. Then what would you do? You would simply write it n21, and the velocity of v1 is 10 and the velocity of v2 of medium second of light is 20, and the answer is 1 upon 2. Okay. Now, after understanding this concept, let's move on to the next slide. Okay, here we are. So in this slide, we will study some other formula related to the refractive index. Okay, there is some other formula to calculate refractive index. So this is formula number first, which we have seen in the previous slide as well. And this is formula number second, where you have to figure out the accurate refractive index of a medium. Let's suppose this is a glass. Okay, this is the glass. This is medium second. And this is your medium first. And you have to figure out the refractive index of this glass. So you have to apply this formula. You have to apply this formula. So what you will do? You will simply calculate the speed of light in the medium first. And here in this case, our medium is air. Okay, whenever we have to figure out the accurate refractive index, we have to take first medium as air. And this is the second medium. This is by default glass, because we have to figure out the refractive index of glass. So let's suppose the velocity here is v. This is the light bending towards the normal. This is v. The velocity here is v. And here in this case, the speed of light is c. The speed of light is c. Actually, the speed of light in an air, speed of light in air is always constant. Always constant. What is the value of constant? This is c. And the value of c is c into 10 to the power 8 meter per second. And you can see this is a very high value. 3 into 10 to the power 8 meter per second. It means it is very, very, very high. So here the velocity of light in air is c, and the velocity of light in glass, let's suppose v. You have to apply this formula, and glass and c upon v. You can calculate it very, very easily. You can calculate the accurate refractive index very easily. Okay, now let's move on to the next slide. Let's try to understand what is clear for us. So guys, in this slide, we will study about the spherical lenses. Okay, what we will study? We will study about the spherical lenses. So when we were studying reflection, we studied about the spherical mirror. The spherical mirror. But here we are studying refraction. That's why here we will study lenses. Okay, so let's talk about the lenses. So in spherical mirrors, there were two types: concave, and convex. So here also you can see there are two types of lenses: convex lens and concave lens. Now, what is the difference between convex and concave lens? Before telling you the difference between a concave and a convex lens, let me tell you one another thing. Sometimes students get confused that concave mirror you can also call them double concave lens. Sorry, concave lens. I'm not talking about mirror. I'm talking about lens. Double concave lens. And here also, the convex lens can also be written as double convex lens. I hope guys you got my point. Now, this is a convex lens. This is a convex lens. Okay. This is a concave lens. Because you can see there are two concave mirrors. What I have told you that concave mirror is the mirror where the light is reflected from the inner side. You can see the light is reflected from the inner side. So that's why it is made up of two concave mirrors. That's why it is double concave lens. And there are here it is made up of two convex lenses. So that's why this is double convex lens. Okay. So guys, now before I tell you some other information about these lenses, let me tell you one thing that the properties of convex lens is very similar to the concave mirror. Very similar to the concave mirror properties. Okay, and the properties of a concave lens is very similar to the convex mirror. Okay, and you will understand this later parts of this topic. But for now on, you just need to remember the properties of concave mirror is same in as convex lens, and the properties of concave lens is similar as convex mirror. Now let's see. Whenever a light, this is a parallel ray, okay, coming like this, and after the refraction, these parallel rays diverge at this point. Diverge at this point. So this is performing, sorry, converge at this point. This is performing converging action. Converging action. But in this case, you can see the light is getting diverged. The light is being diverged like this. So here, the diverging action is being performed. Diverging action. Okay guys, I hope here you got my point. This is converging action and this is diverging action. Now remember the case of mirror. When we were studying mirrors, then we saw that the concave lens performs converging action. But here, sorry, when we were studying reflection, then the concave mirror was performing converging action. But here, the convex lens is performing converging action. Okay. On the other hand, this concave lens is performing diverging action. But when we were studying the convex mirror, then the convex mirror was performing the diverging action. So that's why I said that the properties of convex mirror is similar to the concave lens, and the properties of a concave mirror is similar to the convex lens. I hope guys you got my point. Now let's move on to the next slide. Okay. So here we are. Here we will study some terms related to these mirrors. Okay, so this is a convex mirror. This is a convex, sorry, this is a convex lens. So this is optical focus. So this point, this center is known as optical focus. Optical focus. And this is principal axis. The principal axis is the line, this line, which is passing through the optical focus, like this. Okay. So the center point of a lens is known as its optical focus. The center point is known as optical focus. I hope you got it. Now let's go over to the next slide. So here a line passing through the optical center is the principal axis. Let's suppose this is a concave lens. This is a line passing through the optical center. Now, focus is the point where rays converge or appear to be converging after refraction in lenses. So you can see this is a line parallel to this principal axis. And because this is a concave lens, the light is diverged. Now, this ray is appearing to be coming from this point F1, to be passing to this point F1. This is known as the focus of a lens. Focus of a lens. Okay. Now let's move on to the next slide. Now, here we will study about the diagram. We will study about the diagram, and these diagrams are called ray diagram. Okay. And in reflection also we saw the ray diagram. In the case of mirror, the same thing we will see for the lenses here. Okay guys, I hope you got it. Now you have to remember that in the case of mirrors, there used to be only one focus. But in the case of the lenses, there are two focus. So we refer them F1 and F2. This is a F1, this is a F2. This is a F1, this is a F2. There are two focus. And similarly, in the case of mirrors, there used to be a center. But here, there is no concept of center. We will write center from 2F. Here 2F1, here a center will be written as 2F2. Okay, here it will be 2F2. And here 2F1. Okay, 2F1. So now, this is the first rule. What happens according to this rule? Whenever a parallel line parallel to the principal axis, a parallel ray to the principal axis comes like this, and after the refraction, it passes to the focus of the convex lens. You can see this is a ray parallel to the principal axis. After the refraction, it is passing through this point F2. Now, in this case, the case of concave lens, what is happening? A ray coming parallel to the principal axis, and after the refraction, it is diverging like this, but it is also appearing to be passing through this point F1. It is not actually passing from here. It is appear to be passing like this. Okay, so that's why you can simply say this is the rule first, that whenever a line coming parallel to the principal axis, after the refraction, it passes to the point F, or the focus of the convex or concave lens. Now let's move on to the next slide. Okay, so this is the second rule. This is the second rule. And according to this rule, what happens that whenever a light passes through the focus of a lens, become parallel to the principal axis. This is your principal axis, and after the diffraction, this line which was coming from this point F, or which was passing from this point F, after the diffraction, it becomes parallel to this principal axis. Now, same thing will happen in the case of concave lens. A line is coming like this, and it is appearing to be passing from this point F1, F2, but it is not actually passing from here. It is appearing to us that it is passing from F2. Now, after the diffraction, it will become parallel to the principal axis. I hope guys you understood this rule. Now let's move on to the next slide. Okay, so here we are. Now this is third rule. A ray of light passing through the optical center goes straight without changing its path. It's very, very important. that you have to remember that whenever a light ray passes through the optical center, it goes without changing its path. It will not bend. It will go without changing its path. And the same thing will happen in both the cases. In convex lens and even in the case of concave lens, same thing would happen. Okay, guys, I hope you got it. Now let's move on to the next slide. Now, here is a question for you. Okay, these three rules have been finished, and I hope we understood it completely, because in the upcoming lectures we will be forming the ray diagram, and we will form images for object at different distance from the from the lenses. Then we have to use these laws of forming ray diagram. Okay, so you have to remember it. Now here is a question for you. Let's solve this question for your understanding what we have learned yet. So refractive index of a glass is 1.5. If the speed of a light in vacuum is 3 into 10 to the power 8 meter per second, find velocity of light in glass. Okay, so guys, you have to remember that the speed of light in air as well as vacuum is always 3 into 3 multiplied by 10 to the power 8 meter per second. Okay, so if this data is given or not, you have to assume the velocity of light in air and vacuum 3 into 10 to the power 8 meter per second. So what we are asked here, we have been asked the velocity of light in glass. Okay, so let me give you a basic idea what this question is saying. So this is a medium second, that is glass, and this is vacuum. Okay, and the light is coming, and when it enters in the glass, it is this is a now normal, and it is bending like this. So we have to answer when we have to calculate the velocity. In this case, we will simply apply the formula, because we know that the refractive index is Nm is equal to C upon V. Okay, and now we have to figure out this C. So we will simply cross multiply it here, and it will become C upon M. Now, what we have given in this question, we have been given value of C, that is 3 into 10 to the power 8 meter per second. We have been also given the value of this refractive index, that is 1.5. So we will simply put these values in the formula and get our answer. 10 to the power 8 meter per second upon Nm, the value of Nm is 1.5. So it will 32 times. So here is the answer is 2 into 10 to the power 8 meter per second. 8 meter per second. So this is the answer. Okay, this is the answer of this question. Now, guys, in the second question, the refractive index of a material depends upon option number A is temperature, option number B is wavelength, option number C is nature of the material, or all of these. Okay, so you have to answer. What is the answer of this question? So the answer of this question is D, because the refractive index of a material depends on all these quantities: temperature and the wavelength and the nature of the material. So the answer here is all of the above. All of the above. Okay. So I hope, guys, you understood this lecture completely. And now I am ending this class, and see you later. Bye bye.